Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will be discussing the design of sequential circuits. In the previous lecture, we discussed the analysis of sequential circuits using the D flip-flop, JK flip-flop, and the T flip-flops. In the current lecture, we will be starting with the design of sequential circuits. Because in this course we are only concerned with the synchronous sequential circuits, so our design procedure is limited to the synchronous sequential circuits. For the design procedure, we will be implementing or doing the inverse of what we have done in the analysis part. Because in the analysis part, we were given a certain circuit, and from that circuit, we were able to represent it in a form of a state table and then in the form of a state diagram. Now, in this part, design part, we will be given a certain design parameters, and according to these design parameters, we would design a methodology. And from that methodology is first represented in a form of a state diagram, and then from that state diagram, we would be representing it in a form of a state table, and then from the state table, we will be representing in a form of a circuit. So we will be following the inverse approach of the analysis section here. We will illustrate that how we could use the different types of flip-flop like D flip-flop, JK flip-flop, and T flip-flops to design a given sequential circuits. The design of a clocked sequential circuits generally starts with some set of specifications or in a form of a logic diagram, which list Boolean functions from the logic diagram can be obtained. It is a bit different from the combinational circuit, because in the combinational circuit, the whole methodology of the circuit is completely defined or specified by the truth table. But in a sequential circuit, we require a state table instead of a truth table to determine or define its specifications. The design procedure of sequential circuits involve few steps. We can roughly write them in the form of these seven steps. The first one is the most important one. The first one is that from the description and specification that are given to us, we derive a state diagram of the circuit. So this is the most important thing, that what we want to do. Say we want to design a sequencer, or we want to design a binary counter. So these are kinds of specifications that are usually given to us. So what we need to do is, the first thing is that we need to derive a state diagram from the functionality that is given to us. And the next step is that if there is a possibility, we can reduce the number of states if necessary. There are some condition or you can say some techniques that are used for the state reduction. We haven't studied them, so we will not be utilizing this step here. But you should know that there are some processes through which we can reduce the number of states. The next step is to assign the boundary values to the states, like we have done. Say if we have a four-state system, we have assigned them the binary values like 0, 0, 1, 0, 0, 1, and 1, 1. So for each state, we have defined a unique value. And then from these binary values, we obtain a state table. The state table consists of multiple entries, which consist of generally you can say a present state and next states, and then the inputs and the outputs. We choose the flip-flop, what kind of flip-flop we will be using to design the circuit. It could be either the D flip-flop or the JK flip-flop or the T flip-flop. And once we have choose the flip-flops, then what we do is we derive the simplified flip-flop input and output equation based on the type of flip-flop that we are using. Once we have derived these equations, then from these equations we can draw the circuit diagram or the logic diagram of the whole process. So we follow this sequence of steps to obtain our final circuit diagram when we are given a certain functionality of this circuit. We will be discussing this process through an example of a sequence detector. Suppose we want to design a circuit that detects a sequence of three or more consecutive ones in a string of bits. Say our system is receiving an incoming bits from say a serial input, and we want to determine that if there is a sequence of three or more consecutive ones in a string. So we have to detect it. How we can do it? We need to first formulate or in our mind that what could be the behavior of this kind of system. The first step is the very important that how we could represent this functionality in a form of a state diagram. There are many ways through which this could be thought that we could do this process. Just realizing that what could be the states in it, we have follow a mechanism in which we have mentioned the four different states of a system. Say we have mentioned the first state as the S0 state, or the you can say the starting state or the resetting state. You can also call it a 00 state. Say whenever if receives an input a zero, our system will remain at the same state. So this is our first state. This is represented here as S naught. Whenever our system would receive a zero, it would remain at the same state. And then when it's received the first one from the input, this is representing the input here. This is so when it would receive the first input here, what would happen? It would move to the next state, which is S1. Again, when it is at S1 and it receives say a 0 again, so what would happen is that our sequence would break, because after 1 there is a 0 occurrence, so our system will again go back to the reset state. So if a 0 occurs or we are on the S1 state, we would move back to the S0 state and our system will start again. Say our system starts again, it detects a 1 in the input, it moves to the next state, which is S1, and then it again detect another one. So it would move to the next state, which is represented as S2. So now we have detected two consecutive ones. Now say if again instead of a 1 a 0 occurs in the input, what would happen is that the system will again go to the reset or the starting state, which is S0. And if it detects a 1, then it would make three consecutive ones. So then what would happen is it would move to the state 3 or state S3. When the system is state S3, our main functionality of the system is now performed, that it is now detecting that there are three consecutive ones. And after detecting the three consecutive ones, what happens is that the state puts its output value equal to 1. So its output value is equal to 1 because its output is only dependent upon the current state. There is no separate circuitry for the output, and it would be asserted once it detects the three or more consecutive ones. So at this point, our system will be detecting that there is a more than two or three ones in this sequence, and then after that, if there are some other ones that are continuing from the input stream would arrive at this system, the system will keep on moving at the same stage, or it will keep the same state as 3. Say whenever the one occurs after this point, it will remain at this state. But suppose if a 0 occurs, then what would happen is that our system will again move to the reset state. So in this way, this whole state diagram is representing the behavior of a sequence detector that detects consecutive ones, three or more consecutive ones in a bit stream. Whenever there is a 0 in between the streams, it would move back to the reset state or the starting state, and the output value is only 1 when there are 3 or more than 3 ones consecutive ones occurring. So otherwise for rest of them the value is equal to, the output value is equal to 0. So from only this statement, the first statement, the first thing that we need to do is that we need to design this basic state diagram. and we can represent it in many different forms. So we can represent any given form in both types of, say, melee and more, depending upon the what our requirements. But if we see this example, it is very clear that it is actually a more machine or the more model, sequential model, because the output here is only dependent upon the current value of the state, or the current state S3, which is represented here as. So it's only dependent upon the state values. If the state values are equal to 1 1, or say S3 is representing 1 1, so whenever the both of them are equal to 1, then that is representing that output should also be equal to 1. Now, this was the first step, that how we achieve this state diagram only from this given or the desired expression, that we have to design a string sequence detector to detect three or more consecutive ones. Now we will be moving on to the next step, that is determining the state transition table for this system. We would be designing the state transition table using multiple types of flip-flops. For this example, we are currently using the D flip-flop to represent this system. Because the functionality of D flip-flop is very simple, because the input to the D flip-flop is equal to the output at the next clock cycle. So we will be first utilizing the D flip-flops, then we would be analyzing these kinds of circuit using the JK flip-flops, and then the toggle flip-flop. So first, what we need to do is, from the diagram that we have designed, the state diagram that we have designed, we need to represent this system in form of the normal state table, which comprises of four sections. First is the current state or the present state, then the input, then the next state, and then the output. The state, because we have seen that there are four states, S0, S1, S2, and S3. To represent four state, we need two bits to represent them. So A and B are representing the states. Say this A, the 00 is representing the S0 state. The next one, 01 here, is representing the S1 state, while 10 is representing the S2 state, and the 11 is representing here the S3 state. We can see from here that because there is an input involved in it, so basically the inputs combination are of 3 bits, so we would have total 8 different combinations. For every state, there could be input could be either 0 or could be 1. So now to determine the next state value, we can determine the values of the next state very easily, because we are using the D flip-flop. So we can just derive these combinations, and from these combinations we can represent that what would be the value of this one. Because if you see the state diagram, from the state diagram, it is very clearly mentioned that once you are in a starting state or the 00 state, and the 0 occurs, we would remain at the same state. So we can easily write the next state here as this one. Instead of writing or calculating the inputs and the outputs of the flip-flops, we would be just mentioning these next state directly from the state diagram. Similarly, if our current state is 00 and we get a 1 in the input, then what will happen is we would move to the next state, and the next state is represented as S1 or 01. Similarly, when we are S1 state and we get a 0 in the input, we would remain at the same state. But if we get our 1 here, then what would happen is that we would move to the next state. Similarly, once we are in the S2 state, which is represented as a 10, and a 0 occurs, we would again move back to the reset state. While if we have a 10 and a 1 occurs, then we would move to the next or the last state, which is S3. And once we are in the S3 state, if there is a 0 occurrence, then our system will move back to the reset state. But if there are continuous 1 coming from the input, then we would remain at the S3 state. And as our requirement was that our system should value should be asserted to 1 once we have three or more sequence of ones. So that's why these values will only be getting the output equal to 1, otherwise the y would be equal to 0. So in this way we have derived the state table directly from the state diagram. And now what we will do is we will try to represent all these equations which are representing the next state and the outputs in a form of input combinations of A, B and X. And by representing them, we would be designing a combinational circuit for three different things. First one is the A, then the B and then the Y. So to represent each of them in a form of a table, what we do is we use the basic K-map technique because our system involves three input. First one is the A, then the B and the X. What we do is we use the three variable K-map here. First, we derive the equation for the input of the first flip-flop, which is represented as DA. We can see from the table in the last lecture that its value is 3 on different values M3, M5 and M7. You see the M3, M5 and M7. So we have placed 1 there and we just solve it through the normal K-map minimization process. This will give us this Boolean expression. Secondly, we would solve it for the next flip-flop input, which is the DB. DB is represented again here as a combination of a simplified form in this form because there are three ones, 1, 5 and 7. We will minimize them using the K-map technique, so it would give us this Boolean expression. For the output, we have only two values, M6 and M7, that are equal to 1. We can see it from the table. So we just need to add both of them to get the output. So in this way, we will derive the equations for the combinational part that is involved to the inputs and the outputs of this sequential system. So now we are representing this system in form of three equations. This equation is first equation is representing the input to the first flip-flop. This is representing the input to the second flip-flop, and this is representing the output equation. Because we were using the 4 states here, so for the 4-state system, you know that you need to represent it in at least two different variables, A and B. Each would be representing a flip-flop. So A and B are representing the outputs of the flip-flops, and they would form 4 different combination, and depending upon their inputs we can easily calculate that what could be the output of the system. Now once we have derived these equations, we now only need to connect these equations in a form of logic gates in a logic diagram to the inputs of the D flip-flop, and then see that we would be forming the overall structure of the system or the circuit for the system. This was our first step, that we were given only an expression that we need to design a sequence detector that detects a sequence of 3 or more consecutive ones. From that statement, we first designed this state diagram. From the state diagram, we were able to derive this state table. It was very simple because if you are given this diagram, you can easily draw it just seeing by the arcs and all these things. You can derive the next state and the outputs. And from these state table, we were able to derive the input equation for the flip-flops that are involved in this sequential system. There are 2 flip-flops, A and B. So each of the input is represented as this, and the output of the system is represented by this equation. Now we need to represent the system in a form of a complete circuit diagram. To represent the system in a form of a complete circuit diagram, we have first represented the 2 flip-flops here. This is the first flip-flop, DA, which you can say, and this is the DB, the second flip-flop. The input of the first flip-flop is corrected as AX plus BX. So X is our input here, Y is the output here. So if we combine this A here with the X, this would give us AX. And similarly, this would give us bx, and we just need to OR them and connect it to the input of the flip flop. So this would give us the first equation. For the second equation, we have ax here, and then we are having the bx, b complement x. So we would be taking the b complement x as this one, and we need to just OR our result. So we would be getting the result for the next flip flop here. And similarly, we have an output here, which is dependent only on the current states of the system. And the current state here are the A and B. So we just need to AND them to get the output. So this is the final expression for the output. So in this way, by using a simple D flip flop, we design a given circuit diagram for a system whose only thing that is given to us is the formulation. The next thing is that what kind of the flip flops that are required to the use required for this circuit. Generally, when a user have to perform this kind of functionality, he's not concerned with the thing that either you are using the D flip flop, JK flip flop, or the T flip flop. He generally needs the functionality to be more accurate. So these kinds of things are generally hidden to the some of the users. So there are some design tools that are utilized in which this kind of thing can be performed by the software itself, that it could be allowed by the software to choose the best of the flip flops by himself. Either it can use the D flip flop, JK flip flop, and the T flip flop, but we should manually know that how we can use each of the flip flops separately to design a given circuit. Kindly do read these pages for better understanding. Thank you.